Welcome to the Deep Dive. Today we're tackling some really interesting stuff about making AI smarter, specifically how we fine-tune these huge language models.
That's right. We're looking at a paper called Self-Evolving Curriculum for LLM Reasoning.
And it gets into something pretty crucial. We know these models are getting good, especially at things like math or code where you can, check the answer easily.
But it turns out how they learn the order of the problems they see the curriculum is maybe just as important as the data itself.
Exactly. And the standard ways. Well, sometimes it's just random problems thrown at the model, which, okay, it works, kind of.
But it's not optimal, right? And then you have people trying to design these curricula by hand, which feels a bit like guesswork.
Yeah, or trying to filter problems on the fly, which just sounds incredibly computationally expensive, like massively so.
And that's the gap this paper tries to fill with this self-evolving curriculum, or SEC.
SEC, okay. So the idea is it learns the best curriculum while it's learning the reasoning task itself.
Precisely. It's an automated approach. It figures out the best learning path as it goes.
Okay, let's dig into this. How does SEC pull this off? The paper mentions something about a multi-armed bandit problem.
That's the core analogy, yeah. Think of different types of problems, maybe easy, medium, hard as different arms or options on a slot machine.
Right.
And SEC tries to figure out which arm, which type of problem, gives the best payout in terms of learning gain at that particular moment.
Ah, okay. So it's constantly choosing the problem type it thinks will help it improve the fastest.
Exactly. It learns which categories offer the most valuable learning experience as the model itself gets smarter.
Got it. So our mission for this deep dive is to really unpack SEC, understand how it works, why it's potentially better, and what it means for, the future of AI reasoning. We're going through the whole paper.
Sounds good. So maybe we should start with why the old ways, these fixed curricula, aren't always great.
Yeah, the paper uses that countdown game example, right? Figure one.
It does. It's that numbers game where you have to hit a target using arithmetic.
And they tried training a model by giving it the super hard problems first, then easier ones, like completely backwards.
Exactly, in a reverse curriculum. And it didn't go well.
No kidding.
The model really struggled to generalize. It couldn't solve harder problems later because it never built the right foundation. It completely hindered its learning.
So a bad curriculum is actually worse than just random problems.
Definitely. And even random. Well, it's better than reverse, but it's still inefficient. You might get too many easy ones or too many impossible ones. Neither helps much.
Right, it's not targeted. And the manual design we mentioned, that's just too reliant on human intuition, isn't it?
It is, and it doesn't adapt. What's good at the start might not be good later. Plus, online filtering is just too slow, too costly.
Okay, so enter SEC. Figure 2 kind of lays out the process. Data gets categorized first.
Yeah, you group problems, could be by difficulty, could be by type, or as we'll see later, even multiple things.
Then what? The curriculum policy picks a batch.
Right. It samples a category based on which one it currently thinks provides the most learning value. Then it picks problems from that category for the batch.
And the main language model trains on that batch using reinforcement learning.
Correct. It tries the problems, gets feedback, usually just right or wrong.
And then the key step.
Yeah.
How does SEC know which category was good to pick? How does it get its reward?
Ah, this is clever. It uses something called absolute advantage, borrowed from policy gradient methods in RL.
Absolute advantage. Okay, break that down.
Basically, it measures how much better or worse the model did on a specific problem compared to its average performance at that time. It's a proxy for, immediate learning impact.
So if a problem from category medium difficulty caused the model to perform surprisingly well compared to its average, that category gets a thumbs up.
Kinda, yeah. The reward for the category is the average absolute advantage of all the problems from that category in that training step. A higher average absolute advantage means that category seems to be driving more impactful learning right now.
Okay, that makes sense. It's linking the choice of problem type directly to how much the model seems to be learning from it.
Exactly. And for the tech folks listening, this ties into the loss function used in policy gradients equation 2 in the paper. Larger absolute advantage means those problems had a bigger influence on updating the model's parameters.
Oh, bigger updates means more learning. Seems plausible.
And they take it further. They show mathematically, equations 4, 5, 6, that for tasks with simple correct and incorrect rewards, maximizing this expected absolute advantage actually pushes the system towards problems the model gets right about 50% of the time.
50%. Wow. Not the easy ones, not the impossible ones, but the ones right on the edge of its current ability.
Precisely. If it's too easy, there's nothing to learn. Too hard, it just fails constantly. No useful signal. That 50% mark seems to be the sweet spot for meaningful progress.
That's actually really cool. It feels very intuitive when you put it like that, like finding the right level of challenge.
It does, and it connects directly to ideas from educational psychology, like Vygotsky's zone of proximal development. You learn best when you're challenged just beyond your current capabilities.
So SCC is automatically finding this zone for the AI.
That's the idea. It's automatically discovering that Goldilocks level of difficulty.
Amazing. Okay, so let's look at algorithm 1, the SEC algorithm itself. How does it put these pieces together step by step?
Right. So it initializes the expected value for each category to 0. Then in each step, it uses a Boltzmann distribution to pick a category.
Boltzmann. So it favors categories that have looked good so far, but still explores others sometimes.
Exactly. There's a temperature parameter, tau, that controls that exploration-exploitation balance. Higher temperature, more random exploration, lower temperature, stick more to known good categories.
Got it. Like turning a knob for how adventurous the curriculum chooser is.
Pretty much. Once a category is picked, it samples problems from that category for the training batch. The LLM does its thing, tries to solve them, gets its reward.
Then the advantage calculation happens.
Yep. Calculate absolute advantage for each problem, average it for the category that was just used. That average is the reward signal for the curriculum policy.
And that reward updates the expected value for that category using TD0 equation 1.
Correct. TD0 is just a standard way to incrementally update that expected value based on the new reward signal. So the system's belief about how good each category is gets refined over time.
And then the loop repeats. Sample category, sample problems, LLM learns compute advantage, update category value, repeat.
That's the cycle. It's constantly adapting the curriculum based on the model's real-time progress.
Okay, proof is in the pudding. Let's talk experiments. What did they test this on?
They used a few different reasoning domains, planning, like countdown and zebra puzzles, inductive reasoning with something called ARC1D, and math problems from the math beta set.
And the models.
Quen 2.5, both a 3 billion and a 7 billion parameter version. They used an RL algorithm called GRPO for the main fine-tuning.
Right. And the results. Table 1 looked pretty convincing, especially for the smaller model.
Yeah, SEC generally outperformed both a random curriculum and a simple difficulty-ordered one. The gains were often clearest on the harder, out-of-distribution O test sets.
ODE meaning problems harder or different than the training one.
Exactly. So for the 3B model on Countdown ODE, SEC gave something like a 13% absolute improvement over random. That's significant and way better than the fixed difficulty order.
Just by changing how it learned, not the model itself. That's the key takeaway, isn't it?
It really is. It shows the power of the curriculum itself. Interestingly, the gains were sometimes smaller for the bigger 7B model.
Why would that be?
Well, the hypothesis is that the larger model is just inherently more capable. It might be able to handle a less optimal curriculum better because its baseline reasoning is already stronger.
Makes sense. A stronger student needs less hand-holding. But that difficulty-ordered curriculum often did poorly, even worse than random sometimes.
Yeah, that highlights the issue with fixed schedules. They just don't adapt. What's easy or hard changes as the model learns, but a fixed schedule ignores that.
And Figure 3 visualizes how SEC adapts.
Right.
It shows the difficulty level it chooses over time.
Precisely. You see a clear trend. It starts easier, then gradually increases the difficulty across all tasks as training progresses. It learns when to push the model harder.
And it pushes the bigger 7B model harder than the 3B one.
It does, yeah. You can see it selecting tougher problems on average for the 7B model, which shows it's adapting not just over time, but also to the inherent capability of the model it's training. It's like a personalized tutor.
That adaptability is really the core strength here.
Yeah.
Did they try it with multiple categories at once, like difficulty and problem type?
They did. They called it SEC2D. They used it for multitask training across Countdown, Zebra, and ARC, categorizing by both task type and difficulty.
And how did that go? Figure 4.
It also outperformed the random baseline in that multitask setting. The learning curve for Countdown Ode was particularly interesting. Random started okay, but then kind of collapsed.
Collapse.
Yeah, performance dipped, maybe because it couldn't balance learning the different tasks effectively. SEC2D, however, showed stable, consistent improvement.
So it's better at juggling multiple learning goals, too. That seems really important for practical applications.
Definitely. And one more thing. They checked if this only worked with their main RL algorithm, GRPO.
Ah, table 2. Did it work with others?
Yes. They tried it with PPO and RLOO on Countdown, and SEC still provided benefits over random. So the principle seems robust across different RL methods.
Okay, stepping back then, what does all this mean for like the future of AI reasoning? What are the big implications?
Well, I think it's a significant step towards making RL fine-tuning more efficient and just more effective, especially for complex reasoning. Automating curriculum design is huge.
Reduces the need for human guesswork.
Exactly. And potentially leads to better generalization models that can tackle harder, novel problems because they learned in a more structured, adaptive way. It could unlock more robust, maybe more generally intelligent AI.
That's the goal, isn't it? More adaptable, capable AI. But it's not perfect yet. What are the limitations?
Right. The researchers are clear about that. Right now, you still have to define the categories up front, like difficulty or problem type. Automating the discovery of the best categories would be a big next step.
So the AI figures out how to group the problems itself.
Potentially, yeah. Or maybe using embeddings or other ways to define the curriculum more flexibly. Also, SEC introduces its own new hyperparameters, like that temperature tau, which need tuning.
Always more knobs to turn.
Always. And they also suggest exploring things like incorporating uncertainty. How confident is the system that category X is really the best one right now?
So still lots to explore. But overall, SEC seems like a really positive direction.
I'd agree. The key takeaway is this dynamic, automated optimization of the learning path itself, adapting in real time to the model state.
It's fascinating how it mirrors good teaching practices, finding that just right challenge level, that zone of proximal development idea again.
It really does. Which leads to maybe a final thought for you listening.
Yeah.
If this kind of adaptive, self-correcting learning process is so powerful for AI, how much more could we leverage these ideas in other domains? Think about human education or skill training.
How can we make learning experiences more dynamic, more personalized, adapting moment to moment based on how the learner is actually doing?
Exactly. It's a compelling question, inspired by seeing these principles work so effectively in training AI, something to definitely chew on.
Absolutely. Well, this has been incredibly insightful. Thanks for walking us through SEC. We'll definitely link the paper for anyone wanting the full details.
My pleasure. It's exciting work.
Join us next time for another Deep Dive.